I'm going to start recording the session. Assignment 5 is uploaded since yesterday. I hope you had time to read it. This is a fixed bed, which is a new topic. I think you started this 1 or 2 weeks ago, I guess. The fixed bed is this topic. It's chapter 3 of the notes. In this case, we have a fixed bed, and what we are seeing is that this fixed bed has 3 zones: an entry zone, a catalytic zone, and an exit zone. And in the notes, I'm showing you chapter 3 of the notes. I hope you're able to watch it. What we can see is that all the derivation for these formulas are step by step in the chapter. That's why I said this tutorial is going to be rather short, because there is not a lot to explain. It's mostly you to read this chapter. And as you can see, here is the drawing and the principle. By now you should be familiar with this exercise that is just a balance, and you have a balance in a height set plus the balance in a higher height set plus delta set, and this is the transport coefficient, and you have this concentration change or the gradient of concentration with the height, and then you have the radial dispersion. And from here you take also the change in concentration. I think this must be volumetric flow, if I'm not mistaken. If I'm mistaken, please tell me. And so on. What I'm trying to say is you already saw this in class, and from all this derivation you get to this, and then from here, taking the Peclet number relationship with this, you get to this, right? And here are the assumptions you made for this equation to be. And this is what we were saying. There is an entry region, a reaction region, and an exit region. So the entry and the exit have the exact same behavior, and all the magic happens in the reaction region, right? So please just go to the notes, read this section, review. I'm not completely sure if this is lesson 6 or lesson 7, but I'm sure you will be able to find it in one of those two. And the assignment, it talks about this fixed bed reactor, and it can be represented with a PFR with axial dispersion, which just means that it is not perfect. And we have the kinetic reaction, and then we have the 3 regions as we just described previously. You have the equation for the entry, the equation for the catalytic part with the reaction included, and the equation for the end region. And you have these conditions. There are boundary conditions that you have to apply, but also that you have to explain. So as you can see, this problem is mostly about solving these 3 equations. Just to clarify, they are not simultaneous equations because they don't have their own conditions. You have to solve one, and typically from a second order differential equation, you will obtain two terms, each one with a constant. That's how we usually do it. And then let me just say something about it. Usually what you do is you write this in terms of m squared minus something m equals 0, using uh, the numbers here and here as coefficients. And then you solve for m, you find the eigenvalues, and m will have two values. M1 it's equal to something, M2 is equal to something, and then you go and write a solution that is going to be C1 e to M1x. Well, in this case it's z, sorry. Plus C2 e to the M2z. This is how typically a second degree, sorry, a second order differential equation is solved, and it's extremely easy. So I don't even want to go into the details of that. I'm sure you will have a good time solving them. Once these equations are solved, you will have 6 constants, 2 from each equation. And these boundary conditions will help you to determine the value of those constants. Again, this could be a perfect sample of an exercise for a differential equation class. It's just that, solve the differential equation. You take the value of c for the first equation. Well, talking about that, when you are in c minus infinite, you have to assume this is the entry region. And I'm not going to say what this means, but this is something you will have to talk about. I'll go to that point there. And then you have this C star evaluated in 0 minus something, and then equals to C star evaluated in 0, let's say in the top side, and in the under 0 and over 0. What I'm trying to say, with not a lot of success, is that this condition represents the line in between two regions. So from 0 minus to 0 plus, and the same for this one, what you are having here is the interface between two faces. 0 minus, probably you already know this, but I'm trying to help those who don't. 0 minus means the approximation to the interface through the entry region, which if you have a line and this line is the interface, and you say this line is equal to h0 or z0, if you approach through this side, you will approach through the negative numbers, the negative values of z. That's why this is an approach to the 0 by the negatives. And if you approach through the top, you will be approaching through the positive numbers, and that's why this is 0 minus and 0 plus. That's it. With these two, with 4 and 5, you have exactly the same, but in this case, you have the approaches to 1, and in this case, 1 is nothing else but the other interface. That will be the interface between the reaction region and the exit region. If you approach to the negatives, it's under. If you approach to the positives, it's on top. Does that make sense? Is that clear? Am I explaining something too obvious, maybe?
Just one question. Why are
Yes,
they, if we're approaching from different sides, why are they equal to each other?
That's a very good question that you will have to answer. But it's not a big deal. And let me tell you why.
Sure.
Um, I will tell you the logical answer. You will have to put this in terms of what's happening inside the reactor. Uh, the difference between the approach in the minus and the approach in the positive should be talking about a very, very small region in the reactor. And in this case, if you approach to the interface, let's say under the exit, and if you approach over the exit, the concentration in a very, very close region to that interface should be the same. Um, that's as much as I can say. But again, let me keep going. It is also known that particles and the entry and exit region have the same size, shape, etc., etc. This is just like an idealization. So explain the meaning of both the differential equations and the boundary conditions. And this is what I was saying. So first, um, first problem is to actually solve these equations and apply these conditions to determine the values of the six constants. That's pretty much it. And then, in a more theoretical approach, uh, we want an explanation of what each one means. That's why I cannot tell you why exactly this is equal, but it will be easy for you. So, what I want in this second part, explain the meaning, is that you go through the terms. If not the equation itself, you could work with the way you derive the equation, right? So, what I would recommend you to do is, as always, start from the very beginning to derive the equation. Once you get to the final equation that you are going to present, you can just number them and solve them. And this will help you because that's problem one, part A. For problem B, for part B, instead of rewriting everything, you can just say, like, taking into consideration equation 5 from the previous part, we can say this and this and this and this and this and so on. So I think that makes sense. We are just I am just offering you a way to not having to do the equations twice. And there is a hint. Uh, and they say that someone did this before you guys, and the name of this someone is Wegner and Wilhelm, and their conclusions are these. Actually, this is the solution of the system. Okay, so this is the solution for the first equation. As you can see, this would be the solution for the second equation, with GO being this. And this is the solution for the last equation. And as you can see, I'm giving you the solutions. So as I said, you have to solve this equation, and the solution is this one. Why do I give you the solution if I want you to solve it? Well, because the point for me is not for you to find this number. You could do that with software. I think Wolfram Alpha can solve it. My interest here is for you to understand where the equations come from, and especially what these conditions mean. And for that, I have a very good recommendation. If you go to the end of this chapter 3, hmm, wait, no, it's not the end. I'm sorry. Give me 1 second. Let me find it. It's one of those things that I had it and then I lost it. Okay, yeah, I know what I lost. Just please bear in mind that this is a further section in the book, but it will help you. Um, this is from the chapter 3, section 2. So this is the two-dimensional model. In this case, you will have to consider Z and R, both of them. So this is not yet what the homework is the assignment is actually asking you to, but in this part, the the boundary conditions are actually very well explained. So this section, the boundary conditions of this, can help you to understand the other boundary conditions. Um, some of them will be pretty obvious and logical, like I guess this one. Uh, I probably should mention this, that you need to take into consideration these values or these substitutions that were made in the equation for this to have sense, to make some sense. Like if you ask why this is 1, C star, why is this 1? Well, if you come here and see the definition of C star and you say that this is equal to 1, then you can draw a conclusion. And the conclusion will be because the concentration is something, right? I kind of gave you that. Okay. Um, again, do that with this one is actually the same as this one, but in this case, as I said before, in the interface and so on. And this one is a very interesting situation. What does it mean that this number is finite and not infinite? Okay. Uh, one thing that I would recommend you to do is to read the actual paper by Wegner and Wilmer. I provide you this paper. I help you a little bit there so you don't have to look for it. As it's mentioned here in the assignment, these are the results obtained by him, and this is the paper. They use a slightly different nomenclature, so you will find that they use F instead of C, for example. But just pay attention, you will see. And they actually explain, again, this is another source for you to read. They actually explain the boundary conditions very well in the paper too. Um, so here's the boundary condition and an explanation and so on. These are the equations, and these are other boundary conditions, are the same boundary conditions we're using, and I just recommend you to read the paper. These are the results that we're presenting. This would be this one using our nomenclature. Um, and then this would be the second answer. And they have some important things to say here about F evaluated in 1 and F evaluated in 0. You may need to recall these values for your homework or for your assignment. Sorry, I keep calling homework. Anyway, and that's pretty much it. So as you can see, again, it's just solving the differential equation, applying the boundary conditions. That part, I believe, is kind of easy. It takes like 4 or 5 pages of algebra, but I believe it's not complicated. It's just tedious, especially because you will end up with six constants, and those six constants will form like a big system of like a 6 by 6 equation, simultaneous equation system. Yes, Nicholas.
Last time I wanted to ask you, is there like a procedure to make the constants? I mean, like a group for you, like same units or somehow related. You know what I mean? Or anything that I see that is a constant, I can just uh, put it in a group and make a lambda or theta or any constant.
Now I get it. Uh, because I was talking about the constants of the differential equations, I was confused about what you were saying. No, there is no rule. You can group whatever constants you want to, um, and simplify your equations as much as you want to. Just it won't be much room for that, at least at the beginning. I believe I used one, like I did one alpha or something. Um, Wait, so I did like, so these are the solutions and these are the boundary conditions, and then I start pulling out the boundary conditions, and in some point I use, yeah, alpha. But again, you can do whatever you want. I'm not saying you have to do it like this. I usually I like to do this because then I kind of simplify things for me for later. And in some point, I had to use the value from the paper. That's what I was saying. Hmm.
All right.
Okay. Oh, you didn't see what I was showing you, right?
No, we
Oh,
had the other screen.
oh. Sorry. Give me 1 second. Okay. Any questions so far? I think it's pretty straightforward, right? So recommendations: read the section 3 of the notes, which is actually very well explained. It has the derivation for the formulas step by step, which will be helpful for you. I will also encourage you to review maybe lesson. Again, I'm sorry, I'm not sure. I think it's lesson 7. You could tell me, but you have been
It's in
quiet.
lesson 6.
Oh, okay, lesson 6. Thank you. And I will encourage you also to read the paper because the paper has everything. And the paper I uploaded to OWL in case you didn't notice. So I think that will be all. Uh, I don't see what else I could tell you without actually telling you the answers, and I don't want to do that. Do you have any questions? Perfect. So in that case, we'll leave it here. I will. I'll say thank you guys for coming and for paying attention. In case someone wants it, I can upload the video, but again, I don't see a lot of value on the video, but I can do it if you want. And um, I'll guess I'll see you next Thursday. I said it right. Yeah, Thursday. So let me see. I think I have a question. Oh no, it's not a question. Just a quick reminder, friendly, extremely friendly reminder. Please, nobody feels like I am pushing you too much. Don't forget to send me abstracts so I can start reading some of your work. I already approved one abstract. If you already have something, we can start discussing the title, let's say, and then send me an email. Say, hey, I want to do this, and I can say, okay, that looks fine. Send me an abstract and so on. And I mean, the 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 earlier we start this, the sooner we will finish. So that will be all for today. Thank you very much and have a great day.
Okay, thanks, Nicholas.
Yeah, have a good one.
Bye bye.
Thanks.